So who am I? I'm that guy. I teach science. I founded physics education a little while ago now. In this case, I mean, for me, 2004. We've worked with quite a lot of students, several million students. We're probably getting close to 4 million now, I guess. And I really love science. That's the thing. I really love having kids explore their world and find out how it really works. And passionately curious about the world myself, and I feel like I'm very much still a student and will be forever so. I believe. I think so. Beyond retirement, all the way through. It's a wonderful place. And it's great to
It's a
discover
darn
some
good
things.
place to be in. It's always filled with a sense of wonder. Makes the world worth exploring and experiencing for sure.
Oh, absolutely. And yes, and to your point, yes, I very much enjoyed coming to California earlier this year to 20 odd schools, looking at states of matter and helping those students in Lodi and in Stockton prepare for the upcoming test for grade five of the California Science Test. But what we thought today is let's think about what's really in an experiment and then how might we actually link this to literacy and numeracy. Now, it doesn't matter what type of experiment we might explore, there are really only three things. There really are, and they're up on your screen. There are only three things that come down to how science truly works. It doesn't matter if you're a multi-million dollar laboratory or a small little classroom, it does not matter. It is, what do you want to test? What's your best guess? We call this a hypothesis. Maybe you might call this a prediction. Best guess, doesn't matter. It's like, what do you think might happen? In simple words. And as you set up your experiment, there's these things called variables, these things that we might control, things we might test, things we might measure. And that's important. Of course, as we're doing the measuring, there's going to be data picked up. And it's our job as scientists, irrespective whether you're 10 years old or a tenured professor, it doesn't matter. You still want to collect that data and you want to analyze it and think about, well, what does this actually mean? That's the important part. But something I was sort of thinking about, Ted, and I thought we might have a bit of a chat about this, is, well, what makes a great experiment? I mean, there's plenty of experiments out there, but what's a great experiment from the student's perspective? What makes it great to them?
Well, for me, it's almost like a great, what makes a great magic trick, right?
Yes.
The draw drops. It's like there's some wonder there, right? It's like maybe it's something that you weren't expecting. And so I think a great experiment, at least for the younger ones, is to kind of shock them a little bit. But I think data is important, right? That you're actually able to get some information, then maybe quantify what you've experienced. And so, being prepared probably makes a great experiment too, right? Just knowing that you've got it all lined up and you know what your hypothesis is. You're not just starting to, mix things together with what's going to happen next, right?
Yeah, exactly. So, in fact, actually, as you're watching this recording, whoever's sitting there, uh, put that up on your interactive whiteboard or whatever you might teach with to your students, and just ask your students straight up, what makes a great experiment to you? It might be interesting to see what they think a great experiment is. In fact, a very classic thing that's been done for many years is lining that question with what is a scientist? Draw a scientist. And you watch them draw old men, generally white, in a lab coat, crazy, wild, Einstein type hair, blowing something up. So you kind of think about what's a great experiment from the student's perspective and what do they think a scientist looks like. And now you've got a bit of an idea of where they're coming from. Because once you know where they're coming from, it really will help you a lot in your teaching. And for me, I mean, everyone's going to have a different perspective of this, but I thought prior to this recording, I thought we might have a bit of chat about, well, this is what I think makes a great experiment. Ideally, it should provoke something. It should be eye-opening. It should convince you that perhaps the world might work this way based on the data I'm seeing. Right in the very center of our screen is something which I love doing with students, is presenting a concept or an experiment that is counterintuitive. It goes against their expectations. That influences them. And it's to me that's an amazing moment when you see kids' jaws drop and it completely goes against their idea. They've had their guesses and it goes out of the way. And oh my gosh. I mean, of course, as scientists, we want to make sure that it's rigorous, it's methodical, it's analytical, but it's those little wonder moments that really, really, really make the difference. We don't want to be bland. We don't want to be beige. So, what I thought we would do is explore a very simple experiment that all of you, no matter where you are, have. We've got ice. We've got ice. Ice is around. Now, ice does some strange stuff. Now, we know that ice is a solid state of water and it's very much bound up. And kids, whether in grade 1 or grade 10, will happily tell you it can melt. Great. We understand melting. But what I thought we might do is explore, and I'll come off the share screen for a moment, is explore a very simple experiment you can try, even try it at home after watching this. Go and get some materials and we'll explain as we go along. It goes against your expectations. So I better, let's do the experiment and see what I mean, Ted. So I'm just going to do the whole swap of my, my thing here. There we go, done. And I'm still here. All right, so what do I have? These black blocks are different materials. And if I drop it, oh, it shudders the things because it's heavy, it's dense. That is a piece of metal. In my country, Ted, it's aluminium. In your country, it's aluminum. Either way, it's that light, flexible metal. They've coated it black because we're doing a fair test against plastic. Plastic, aluminum. They feel different. It's not just about their mass. I mean, that's certainly a heavier block. But they feel different. When I put my hand on this metal, it feels cold. And when I put my hand on the plastic, it feels warm. And so the question to the students would be, if I had some ice, and hopefully if we're doing it perfectly well, they'd be like the same size, all the things. If I have my ice and I put them on these blocks at the same time, which block's going to melt the ice faster? I mean, one feels cold and one feels hot. So kids will have their hypothesis, their prediction, their best guess, and I'm just going to get my hands and grab the blocks and pop it on. Whoa, already. Now, it's a little bit hard to pick up on camera, but you can see a little wet, sliding all over the place. The thing that feels
looks
cold,
like it's melting.
oh, yeah, and it's crazy fast. In fact, it came on the edge here. It's actually hooked itself onto the edge of that. It happened so quickly. I put it on the side there, and off it goes. It's nuts. It's kind of going. Now, of course, if we're going to be fair about this, what if I'd swap the blocks over? I mean, this is probably potentially unfair in some ways, but hang on, that stopped, and now the other one's going. So it's not something inherently different about the ice cubes. It's clearly melting faster on the colder block, which I promise you, if you do this in front of students, I don't care their age, this really can throw kids massively, especially when they feel it first. Now, of course, not all of us are going to have the same size blocks of metal and plastic. I get that. But I'm pretty sure that you'll have baking trays at home, and if you don't, someone else does in amongst your colleagues. Get a rubber baking tray and get a metal baking tray and repeat this same experiment. You will see that the ice melts faster on the metal block compared to the plastic. And so you might be wondering, as you sort of sit there watching this recording, why should I care? What does this matter? What does this prove? Fair question. I mean, scientists really want to understand how the world works. In this case, we're really exploring how heat genuinely moves. Now, I was incredibly careful to say it feels cold, feels warmer. Now, if you think about it, those blocks are in the same room. The room has a temperature. So from a logic point of view, they're rather the same temperature or very close to it. I mean, of course, you could get one of those measurement devices. You could, one of those scanners, and just see if it's truly the case. There might be some fluctuations here or there, but as a whole, it's in the same room. And yet it feels colder, which means to students, when they feel something hot or feel something cold, they think the hot thing's going to melt the ice faster, and I get it. But it comes down to that heat really moves from where it is more heat to less heat. That's what heat does. And the reason my hands feel cold on the metal block, why your hands feel cold on a metal thing, especially in winter, heat leaves your hands. As the heat leaves your hands, your thermoreceptors on your hands register that and you feel cold. So, why did the ice melt? Well, it's drawing heat into the ice cube from the desk. Whereas the plastic, and I mean, I feel like I'm just talking to a face right now, so you might as well let's go back to our experiment here. Literally, the heat from the desk is being drawn up through the metal and into the ice cube. The aluminium, the aluminum, is an incredibly good conductor of heat, whereas the plastic's not that great. It's actually an insulator. I mean, look, it's just sitting there. In fact, by the time I finish this chat here, Ted, this is going to be a puddle. It just will be.
It sure looks like
But
it, man.
and this way hasn't done much. It's just sitting there. So I guess the real question at this point is, sure, we've done a science experiment, and if we're doing a heat energy unit, it's very easy to say, well, let's move on to the next experiment. But I truly, truly believe that science is a genuine hook for all learners,
Hmm.
all interests, all abilities. It doesn't matter where they're coming from. There's something to grab their attention. So as we go through school, we know that numeracy and literacy is like the top notch thing that we've got to get for students. We've got to do this. So let's explore if we were going to use this same experiment in an English class. How might this be pulled apart and used in traditional English teaching? And I'd love to know, as you're watching this, maybe you could write into us and say, hey, I've got this other idea I could use these experiments with. That'd be lovely to know too. So I'm going to quickly share the screen and we're going to have a bit of a chat. Okay, so we did the ice melting speeds and we're going to explore some literacy. Now, of course, we could write an essay. What happened? Explain what happened. Describe and inform the reader. This is what I saw happen with the experiment that Ben just did on his desk. That's a fair thing we could do. But there are other things we could do as well. I mean, we could have a persuasive text. Now, what I mean by this is, when you have debates, and there are plenty of debates in this world, but what if prior to the experiment, you challenge your students to write a persuasive text, or maybe even had a debate in the class? Pros and cons. I mean, yeah, there's a science basis to all this. It's a science experiment. And yet there's an opportunity here now to argue against each other. Well, let's use it. Why not? And now there are other ways that English text can be around. I mean, we could do narrative. Now, this is for the creative types. Is there a plot, a story that can be created that has some form of conflict or resolution that, I know it's a bit odd to
There you got
like,
me there, Ben. That will be a lot of fun, right? And the our students that have their creativity unbound like that, I think if they're given an opportunity, can come up with some really fun things.
oh, for sure. I mean, the large ice cube versus the small ice cube, or whatever it, yeah, the mean metal, or whatever you want to call it. It doesn't matter.
Well,
They're
it's the
exploring their
hero's
world.
journey or something, right, Ben?
Exactly right. I
Yeah.
mean, literacy is designed to help people be literate, and so this is a great way to play with language. I mean, speaking of language, I mean, sensory observations. I mean, if they can be descriptive in their text, putting their hands on the ice and on the different materials, there's an opportunity to describe what on earth they're experiencing, not just for the young kids. There are ways to explain what they're describing for older students too. Now, as we go this through, there's a lot we can do. We could reflect on that personal experience of I thought this, and now I think this based on what I saw. I mean, reflection is an important tool. I mean, of course, being a scientific experiment, a report is rather predictable, and yes, they have a formal structure in scientific writing. That's very true, but they could look at the deep research behind why does heat move from hot to cold. It's an important skill. I mean, English is not separate to science in any way, nor any other language is separate to science in any other way. So they could do a journal, I mean, this could be like after they've seen this, they can start jotting down ideas and thoughts about what they might explore now. Now they've discovered this particular concept. But we could go even further, right? We could even get into poetry. In fact, I know of some poetry and science competitions that are global that researchers compete in, students compete in. That's a lot of fun. Now, that's just 8 real quick titles on the screen. I'm sure that as you might be watching this, that you could think of others. I'd love to hear other ideas for you. We're not bound just by it being an experiment.
There you
We're
go.
using words to do it. Yeah. I mean, any thoughts around this, Ted?
Well, I just that it's fascinating. In fact, I'm going to encourage anyone that watches this to go to a colleague in language arts and say, "Would you run this experiment for me?" Right?
Yeah.
And see what those outcomes are. You know, that kind of cross classroom experience, I think can do a lot. The reflection. I mean, we can talk about each of these points, but I think case well made that any kind of experiment, if we just begin unpacking it, leads to so many other reinforcing skills, in this case, literacy. Now, I guess you've done the same thing for mathematics as well when you thought about this
Yes, we
experiment.
have. Absolutely. Let's pop on over there. So numeracy, there's some parts to numeracy for our mathematics teachers out there, and even if you're not into mathematics, you can kind of pick it. We could have measured these ice cubes in multiple ways. We could have measured the blocks. We could have measured the temperature of the ambient temperature of the room. We could have done the measuring. That is a skill. Working mathematically is a skill, and it's in every syllabus in the planet. Now, of course, once they've seen what's happening, you could look at the rate of melting. I mean, how quickly does this block of solid turn to a liquid in a set amount of time? Now, of course, if you repeat this experiment a bunch of times, you're going to get weird inconsistencies of the data. Maybe we might need to do some statistical analysis of that work. But it goes that it's one thing to do the analysis, but you need to depict the data. I mean, there are plenty of different ways of doing graphing. In fact, I challenge you, look up 9 different ways to do a graph. I mean, you watch your search engine and spit it out at you. Do 20 different ways. There are plenty of ways of showing data. Well, showing data is part of working mathematically. It's part of a numeracy skill. And if you think about the geometry of the ice cubes themselves, you could challenge the students. Okay, yeah, from a science end, what might happen if? So we're changing a variable. If the ice cubes were bigger or smaller, but now we've got to explain the story. If we see the data analysis seeing a bit of a change between the small ice cubes not surviving so well compared to the large ice cubes, we can look at surface area and geometry. And now we're really playing with some shapes here. Unit conversion. I mean, I'm very aware that there are units that we could have measured this in. It could have been in metric or imperial. It could be all over the different ways. Having kids able to change their units of measurement, understanding number lines, is a fundamental skill of, you can't do the advanced stuff without understanding your units in the first place. In fact, as I think, Ted, going through my science degree, it was deliberately set up so that if you didn't understand your units as you were changing between different experiments, you could mess up your university experiment. So this is really important to do.
It is,
And
and
finally,
there's some stories, yeah, definitely stories of cross-cultural research engineering in which different measurements were used that ended up with disastrous results. A rocket flying upside down, for example, I think is one classic
yes.
example. I mean, a really big rocket. You just look at like geometry, for example. That could even be an engineering challenge when you think about it, kind of taking the math and applying it, asking students, could you change the shape to regulate the melting, right? In this
Mm.
case, the aluminium, as you say,
It's,
would be the challenge to kind of regulate it like your insulator of plastic. But
oh, for sure.
fascinating.
Absolutely. And based on that experiment that you just suggested, as you gather the data, you can put this into a model, into a predictive model. And these days, modeling, environmental modeling, is a big deal if we think about climate change and whatnot. Now, we've just looked at the major components, literacy and numeracy, which threads throughout schooling life. But let's be honest, school is not just literacy and numeracy. It's a heap of different subjects, right? They're all over the place. Now, this is me just riffing just prior to this chat, just thinking for me, well, there's a bunch of different areas of subjects that kids might look at, and I'm not going to read it out. I don't want to read a slide out to everyone, but you can kind of see if you have a play with the concept of ice melting and apply it in a creative way to a subject, you can shove an experiment into every area of school, and it doesn't have to be an outlier. It doesn't have to be, you know, really incongruent. It doesn't make any sense. Why are we doing this? You can just use it as a hook. And so, I mean, even the economics professor, like, really, you could do an ice melting experiment, but suddenly now we're talking about coastal towns or ski resorts, and then the economic effect of ice melting. It's a real thing. So I truly believe that science is a hook. It really is. Learners love the visual. They love something happening. They love a questioning result. It's fundamental to human nature. And that means that we can use that creativity, their interest in things in every subject, which means if you've got 30 students in front of you, all with 30 sets of interests, you're very likely to be able to grab their attention using science.
Ben, we're really grateful. You've compiled over your 2 decades of experience more than 150 of these kinds of experiments in which you've recorded sessions like the session we've just done. And you've kind of walked us through some of your philosophy and how we map it back to things like numeracy and literacy. But I guess in February, you're going to be in the UK in January, but in February and March, you're probably going to have a crew out in the United States, right now focused in California. But I think with proper planning, there's no reason why they can't meet you in Florida or in Texas or out in Wisconsin or wherever you might be. For our guests coming from overseas, that might take a little bit more work if you're in Portugal or Sri Lanka. But we can always do it remote, and that's one of the benefits of the work that we've been doing together. Again, for any of you districts out there, if you're in a rural part of the world, and you need a digital science teacher, Ben's the guy. Feel free to send your comments and definitely check out the science dashboard at Magnitude.io. Ben, thank you so much for joining us again. And I'm looking forward to just more exciting experiences with you, both in person and digitally as well.
Much appreciate it. All the best. And all the best to everyone listening on in.
Fabulous. Thank you, Ben.